Okay, let's start in on chapter 20. We'll be talking a little bit more about sound. I kind of went over some of the stuff in chapter 19, but I'll talk about what sound is, how sound's a longitudinal wave, how it propagates through medium, and so how sound works in air. I'll talk about the speed of sound in air, relatively important. I'll talk about how sound can reflect, how it can bounce off the surfaces. I'll talk about how sound can refract, how it can bend. I'll talk a little bit more about energy in sound waves, because all waves transmit energy from one side to another. And I'll talk about how we can force vibrations on various things to produce sounds, and everything has its own natural frequency, which is also related to resonance. And I'll kind of finish off by talking about a little bit more about some applications of interference, as well as the concept of beats. So sound is a wave, and it's going to transmit energy, whether or not we can actually hear it with our ears. So there are sounds that are below our range of hearing, sounds that are above our range of hearing. Now, sound, or any wave really, can interact with objects in three different ways. It can scatter. So if I had a wave kind of coming in, and it bounced off there just like this, then I would say that that wave scattered. The wave could be absorbed, in which case it would probably warm the object up, because energy cannot be created, it cannot be destroyed. And sound can also refract, it can bend, so maybe it would go like this if there was a temperature gradient or something like that. Now, how do we produce sounds? Well, most of the time we have something that is forcing some vibrations. So in the case of a piano, we usually have some strings, same with a guitar or a violin. We could have a vibrating reed like we would have in any wood instrument like a saxophone, or we could also have just a tube, and that tube would have some air that is resonating. It's being driven at a certain frequency, so that would be kind of your wind instruments. We can also have things, other membranes that vibrate. We could have like vocal cords or speakers or something like that. So pretty much what we need to create sound is we need some type of vibrating source. Now, when we talk about stringed instruments, what we often talk about is we talk about the frequency, and the frequency is going to depend on a couple of different things. It's going to depend on the length, and it's going to depend on how massive the strings are. And whenever you take a look at a guitar, there's kind of a reason why guitarists mess around with the length, and there's also a reason why they mess around with the mass. Different masses are going to have different frequencies associated with them. It is also going to rely on tension, and what we can do is we can mess around with the tension, and that's going to mess around with the frequency of a stringed instrument. Now, one thing about stringed instruments is air flows around the string relatively easy, and the strings don't project sound very well. So pretty much any wind instrument or string instrument is going to have this thing called a sound box. And essentially all that it really is it's a big honking surface, and that surface is going to get driven by the frequency of the string, and that's going to bounce into all the air, and it's going to project that sound a whole lot better. So that's kind of why we have these things called sound boxes on guitars and violins and stuff like that. So we have our origin of sound, we have some type of vibrating source, and we have our sound wave. Now, when I talk about the physics of things, I very often talk about the frequency, but what everyone hears is actually going to be a little bit more of a physiological creature, let's just say. And everyone's going to hear the frequencies just a little bit differently. So when we talk about the subjective impression, we would actually say that we're talking about the pitch. So the frequency is the physics, the pitch is your perception. Pretty much though, for this class, you can pretty much use those guys interchangeably. Now, what can we hear? The human range of hearing is actually pretty large. We can hear sounds as low as 20 hertz, that would be your bass, and then we could hear sounds up to 20,000 hertz, and those are those really annoying high-pitched sounds. Now, keep in mind that the older we get, we tend to lose the high end, and so we tend to lose, maybe it drops down to 19,000 or 18,000 hertz on the high end. Now, we do actually have classifications. Again, the human range of hearing, we're going to have 20 hertz all the way up to 20,000 hertz. And the human range of hearing is going to be in between those. Sound waves that are below 20 hertz, we're actually going to call that infrasonic, and just frequency is going to be too low. Frequencies that are higher are going to be called ultrasonic, and you're actually going to see these again when we talk about light. I'm going to talk about infrared and ultraviolet light in a couple of chapters. bear in mind we cannot hear these sounds. The sound exists, it transmits energy, but we just cannot perceive it. So what exactly are sound waves? Well, sound waves are longitudinal waves. Remember, for longitudinal waves, we're going to have some particles, and those particles are going to vibrate back and forth, and that's going to be in the same direction as the wave speed. And these are longitudinal waves. These are mechanical waves. These definitely need a medium. They need a solid, they need a liquid, or they need a gas to propagate. So this room right here has to be full of gas. And what's going to happen is someone's going to open the door, and then we're actually going to have what's called a compression. All the air is kind of being compressed together, and the air is going to blow out the window. When that person slams the door shut, then we're actually going to get a rarefication, and the window is going to go in that direction right there. Now this is a bit of a throwback to chapter 19, but suppose I had a tuning fork or a speaker or something like that, and it was vibrating back and forth. I'm going to have regions of compression, and I'm going to have regions of rarefication. I would call this distance right here, the distance between successive compressions, I would call that the wavelength. You could also define that to be regions between rarefication, so crests to troughs. It doesn't make a difference. Everything that I talked about for wavelength in chapter 19 is going to apply for sound waves. So let's talk about how sound waves, kind of propagate. Again, we're going to need something vibrating, so we could have a speaker. And that speaker is going back and forth somewhere between 20 hertz and 20,000 hertz, and it's bumping into the air that is right there. Again, this medium called air has to be there. We would not be able to hear sounds in like outer space, where it's a vacuum. So I hate to, crush any Star Wars fans, people out there, but when you hear the ju-ju-ju-ju, yeah, that doesn't actually happen. And what we're going to have is we're going to have regions of compressions and rarefications. So we're going to have regions, we're going to have a wavelength like this, compressions, rarefications, rarefications, and that medium gets transmitted, and then it sets some other medium vibrating. That medium could be a microphone, or it could be your eardrums, and lo and behold, sound is heard. Now, how do we hear sound? Well, we have our medium. In this case, it's going to be air. And inside of our ear, we have an eardrum. And that eardrum is essentially just a membrane. And that sound, that air molecule is going to bump up against it. Again, the air molecule over here doesn't have to physically make that journey. It just has to bump into this one, bump into this one, bump into this one, bump into this one, and eventually hit the eardrum. Then what's going to happen is we have 3 little bones inside of our ears. And kind of what happens as you get old, these bones get old, and that's why we tend to lose the high end. And then inside of our ear we actually have something called the cochlea, which looks kind of like a snail, and it's got some fluid in there, and that fluid has some hair-like follicles on there, and it kind of sets these guys vibrating, and it turns that into an electrical impulse, which is then taken to the brain. Now, do bear in mind that sound needs some type of medium, and I've talked about gases so far, but we can talk about liquids or solids. Now, if you remember gases, we had individual molecules that were kind of in motion, just by the very nature that they had some temperature associated with them. Now, when we think about liquids, there's going to be atoms where we're going to have chemical bonds, and they're the weak chemical bonds, and they're going to be connected to one another. And probably not surprising that if this guy is vibrating back and forth, then it's going to travel faster in a liquid than it is in a gas, because these guys are connected and these guys are not. So it's going to travel a lot faster in water than it is in air. Now, if we talk about solids, solids are going to be nice, pretty crystalline structures where we have lots of chemical bonds to lots of atoms. And probably not surprisingly, as this guy starts to wiggle, then it's going to travel a whole lot faster in something like a steel than it would be in air, simply by the nature of the chemical bonds. Now, I will primarily talk about sound in air. Air is a gas, and something that we know is that the speed of sound is going to depend on temperature, humidity, wind, and a whole bunch of other things. Now, in dry air, sound travels about 330 meters per second, and that's at freezing 0 degrees Celsius. Essentially, the room temperature is 20 degrees Celsius or so. Kind of a rule of thumb. You could use 340 meters per second, 343 meters per second. Essentially, for every degree over 0, we essentially tack on 0.6 meters per second. And essentially, all that we're really saying is the air is moving faster because it's a little bit hotter, and so sound travels a whole lot faster. Now let's just get a little bit of practice with this. Something that we do know is distance is equal to rate multiplied by time. And suppose you saw someone chopping wood and you heard it 1 second later, then what's going to happen is if it's 0 degrees Celsius out, then they're going to be roughly, 330 meters or 900 feet away. Now, suppose you hear thunder 2 seconds after you see lightning flash. Now, something that I haven't told you is light travels really, really, really fast. Light actually travels at 3 times 10 to the 8th meters per second. So for all intents and purposes, that lightning is essentially instantaneous for you because you're probably relatively close to it. 2 seconds, you would essentially say distance is equal to rate multiplied by time. And you would say, okay, well, 2 seconds multiplied by 330 is probably going to be around 660 meters. Now, I just want to talk a little bit about the reflection of sound. And essentially, I said that sound, when it interacts with matter, it can reflect, it can refract, or it can be absorbed. And reflection is just going to be a process where the sound bounces right off of a surface. And you could even call that an echo. So here we have a speaker, and that speaker is putting out some sound waves, and they're bouncing off of the walls, and some of them are reaching the girl, and some of them are not. If we have multiple reflections, we actually just call that reverberations. Now, the surface kind of matters, and which one are you more likely to hear echoes off of? It's probably going to be the hard surfaced walls. Kind of what you see is what you get, and carpet's going to absorb. Open windows are going to let it go out, and if you've ever been into like an empty apartment, you tend to hear lots of echoes in empty apartments. Now, concert halls care a lot about this because sometimes they want the reflections to occur, and sometimes they want it to be absorbed. So there's lots of studies into acoustics when it comes to things like concert halls. Kind of the rule of thumb is what you see is what you get, and the white surfaces up here, they're going to be really good at reflecting light. The dark surfaces, not light, they're going to be good at reflecting light as well as sound. The dark surfaces up there, well, they're going to tend to absorb both light as well as sound.